Yeah, today we're going to continue our discussion on random variables. And in talking about random variables, we talked about their probability models, the distribution of possible outcomes, and the likelihood that they happen. And so we have a couple special probability models we're going to talk about now. The first one being the geometric probability model. Before we talk about that, we have to understand some things about these types of probability models we're talking about. And so in a geometric probability model, and in our next model we talk about next time, a binomial model, we have to have what we call Bernoulli trials. And for information on why they're named that, you can go ahead and read the PDF of the chapter in the book if you like. But for now, we need to understand what it is to be a Bernoulli trial. And in a Bernoulli trial, there are only two possible things that can happen, and we call those things success and failure. And success is really just the thing we are trying to observe happen, and failure is when that thing does not happen. So sometimes success might actually be something bad, but it's just what we're looking to observe. And so these things have fixed probabilities in a Bernoulli trial, and we label the probability of success P and the probability of failure Q. And I'm going to note here that, of course, they need to be fixed. Fixed means they will not change. And we need to know what those probabilities are up front. So for a Bernoulli trial, we need to only have two possible outcomes, success or failure. We need to know the probabilities of those outcomes, and those probabilities need to be fixed. That means they need to not change no matter what happens. So if I have one outcome, it does not change the probability of success or failure on the next outcome. So they need to be independent. And so if you read through these options, let's go read through these and see if you can decide if they're Bernoulli trials. So what we're looking for is, are there only two possible outcomes, success, failure? Do we know the probability of those outcomes? And will the probability of those change based on a previous outcome? So go ahead and take a pause here, take a minute, and we'll have a quick discussion about them. So if you read through these, the only one that you can answer yes to as being a Bernoulli trial is B. So if we look at this group of pregnant women, they either give birth to twins or they don't. So we call that success failure. In this case, success would be twins. Failure would be, well, they call it like a singleton birth where you have one child, or maybe they had triplets, but we'll say no twins. So again, having twins doesn't mean you're successful, but in this case, we're just labeling that as our success. And we have the fixed probability P of 1 in 90, and therefore our Q is 89 in 90. In A, just a quick discussion in A, the probability of a female being chosen changes because once we choose one female, then the probability of another female being selected decreases. In 3, the probability of having twins changes once you already give birth to twins. You are more likely to have twins. In here, there is not just two options. There's more than two colors in a bag of M&Ms. And we will save the discussion for E later when we get further down the line. So right now, the only Bernoulli trial here was B, where we had a success failure where you either had twins or you did not. So we found expected values for probability models in our last couple lessons, and we found standard deviations. And so that's going to change a little bit here. To find our expected value for a geometric probability model, we are going to take 1 and divide by the probability of success. And for our standard deviation, we have the square root of our probability of failure divided by our probability of success squared. And what we're doing in a geometric probability model is we're trying to find out the probability that our first success happens on an nth trial. That will probably make more sense when we do an example here in a second. So just know this notation that P is the probability of success, Q is the probability of failure. When you look at the formula sheet that we get for the AP exam, they are going to denote failure as 1 minus P. So just get used to seeing both ways of denoting the probability of failure. For us, we're going to use Q, but just know that they denote failure on the formula sheet as 1 minus P, because Q equals 1 minus P. If we subtract 1 minus the probability of success, that gives us the probability of failure. X here, our random variable, is the number of trials before we get our first success, whatever that success is. And then we are going to start using some proper notation here when we talk about probabilities. So this P, this capital P here, stands for the probability of. It's sort of like a function when we talk about algebra, f of x. That's read f of x, function of x. Here we are talking about the probability of x happening. So let's look at an example, and maybe some of that will become more clear. So go ahead and pause here, take a second to read this example, and then we'll go through it. So here we're talking about getting spam emails, and then I guess we'll call them non-spam emails. And so overnight, because you're not checking your mail at home, when you're for your job, you collect emails. And when you look at your email in the morning, we're trying to figure out how many spam emails we're going to expect before we get to a real message. And so we should define what success and failure are for these. In this case, I want to know how many emails we are looking to get to before we get our first legitimate real message. So first, let's talk about these being Bernoulli trials. It is, because when I look at an email, there's only two options. It could be spam or it could be a real message. It looks like we have an established probability based on previous knowledge that 91% of messages are spam. That means 9% of messages are good, important messages we need to see. So we have an established fixed probability. And then looking at one email is not going to change the probability that the next email is spam or not spam. And so we have independent events happening. So I'm going to define success as a real message. And in this case, then that means failure, Q, which is 1 minus P, is 1 minus 0.09, but we already know what that is. That's 0.91. And when we talk about probability, we're talking about a decimal between 0 and 1. This is a geometric probability because we are looking to find our first success. We want to know how many messages we are going to have to look through to get our first success. So when we're asking how many should we expect, well, that means we're going to be looking for our expected value, or our expected value, our mean of this geometric probability distribution. We want to know when we can expect our random variable x to be equal to 4. So we're going to take 1 and divide the probability of success. And we'll get 11.11. So we can expect on average that when we get to work in the morning, we have to look through 11.11 messages before we get to our first real message. I'm sorry, I don't know why I put 4 here. I think I was jumping ahead of myself. I'm sorry if that lends into any confusion. So then we want to know the probability our fourth message is the first real one. So that's where I got my 4 from. Again, I apologize for any confusion. So I'm going to look for the probability P of our random variable being equal to 4. And so there was a formula up here for us to use, and we are not going to use it. You can if you want to, but we have these calculators that do a lot of work for us. And so we are going to go to our calculator, hit the second key, and then vars, our distribution list. I'm going to arrow up to get to the bottom. And you can see the bottom 2 have Geomet. We're going to choose Geomet PDF. And we'll tell the calculator our probability of success P is 0.09. Our X value comes from right here. We want to know our fourth message is our first legit message. And then it's going to put that in there. We hit enter one more time, and it gives us a probability. 0.0678. I like to go 4 decimal places. So on average, we'll expect to go through 11.11 messages before we get to an important one. And the probability that our first important one, our first success, is the fourth email we open is close to 6.8%. 6.8% chance. So it's not very likely, but it's also not impossible that our fourth message is our first real message. Go ahead and pause here, read through this one, and we'll do one more example. So here we're looking for O-negative blood donors, and about 6% of people have O-negative blood. So when I get a blood donor, there's only 2 possibilities here. If we're looking for O-negative, they could be O-negative or not. And so we would consider O-negative a success, not O-negative a failure. Not that you're a failure if you don't have O-negative blood, but right now, for our problem, it would be considered a failure. We know the probability of O-negative blood, P, my probability of success is 0.06, and that makes Q 1 minus 0.06 to be 0.94. So 6% of people have O-negative. That means 94% of people have not O-negative blood. And so my probability of success is 0.06, probability of failure 0.94. My probabilities are fixed. We know what they are before we do this. And the probability of one person having O-negative blood does not change because somebody else had O-negative blood. We can have a discussion in class about here sampling without replacement and how it still keeps our probabilities or our people independent. Somebody make sure you bring that up, and we'll have a chat about sampling less than 10% of the population. So we want to know our expected value, so we can find our expected value by doing 1 divided by P, our probability of success. And get 16.67. And we have units on here, donors. So we should expect to, on average, take blood from 16.67 donors before we get an O-negative blood donor. And then we want to find out the probability that the first O-negative blood donor is found is one of the first 4 people. So this is a little different. We're not looking for our first success to be the exact 4th person, but what if it is one of them? So when we write this out, we want to know the probability that our random variable is less than or equal to 4. So we want to know the probability that our first success is um, less than or equal to our fourth blood donor. So we're not just looking for the probability that our fourth blood donor is a success, we're also looking for the probability the third is, the second, the first. Um, so those 4 possibilities. And so we don't have to do 4 separate problems here. Our calculator is going to help us out a bit. We are going to, of course, do second vars, go to our distribution list. I'm going to arrow up just to get to the bottom. This time I'm going to choose that geometric CDF. C stands for cumulative. I'm going to tell it our probability of success, and I'm going to give it our X value. Here it's 4. It's going to calculate the probability for that X value and everything less than it. So since I have less than, I can make my X value 4. And it's going to give me this probability of 0.2193. So what this is the probability that our first O-negative blood donor is either the first, the second, the third, or the fourth person. Any one of those things would satisfy this. Approximately a 22% chance that one of our first blood donors is O-negative. So that's all I got here for today. Do make sure you stick around and answer the questions at the end. If you need any clarification here, make sure that you ask for help, and then we can continue talking about this together in class.